Now we have studied that. We just completed what? Motor. What was the basic working thing behind motor? That when a current carrying coil is placed in a magnetic field, it experiences a torque. My point is, what we did in motor, I'll draw just rough diagram, that this loop was provided with some magnetic field with some current flowing in it, due to which it started rotating. So my question is, what if we provide the magnetic field and we start rotating it ourselves? Suppose I have a handle here and I keep rotating it. With the same speed it was rotating when the current was flowing, when the motor was working. So do you think current is going to produce? See, what we did initially, we provided current, we provided magnetic field. Rotation is something which we got out of it. If I provided rotation, if I provided magnetic field, do you think we are going to get current out of it? Yes, we do. And that is the basic working principle behind generator. So what is generator? Generator is a device which generates electricity. And how? To understand the whole concept, we'll walk through the whole concept of magnetic flux and electromagnetic induction. Now, what is magnetic flux? Magnetic flux is very simple thing. Suppose this is a magnet, okay? Now we have magnetic lines of force which is coming out of it, right? Suppose I take any random area in front of this magnet from which these three magnetic lines of force are passing. What are the magnetic lines of force passing through this area? Right now it is 3. So magnetic flux is equal to 3. Suppose 5 lines are passing, so magnetic flux is 5. So what are magnetic flux? It is the number of magnetic lines of force which is passing through, or which are passing through a defined area. Number of lines of force passing through a defined area. Now why are we studying about magnetic flux? There was very interesting discovery back in 70s by Michael Faraday and his associate. What they found out was, they were actually playing with the radio at that time. So there was this galvanometer. Okay, galvanometer is a device which detects current. It does not measure current. Current is measured by ammeter and voltage is measured by voltmeter, and both of these devices are derived from galvanometer only. So we do some modifications in galvanometer in such a way that it can be converted into ammeter or voltmeter. Done. So we are talking about galvanometer. So they were working on something, and there they had their galvanometer, and the galvanometer has two connections, obviously, like ammeter and voltmeter. So these two connections were joined. They accidentally dropped a magnet inside the loop, and what they saw a sudden deflection in the needle of the galvanometer, and they were astonished. How is that possible? Because the deflection in the needle shows that the galvanometer has detected some current, but there is no source of current in this circuit. That means the current got produced by itself. This phenomena was then studied in detail, and the phenomena was termed as electromagnetic induction. So what is electromagnetic induction? When electric current is produced by itself due to magnetic field, then the phenomena is called electromagnetic induction. That is the phenomena of production of electric current by changing magnetic field. Now why did we study flux beforehand? See, this is how the observations of electromagnetic induction was taken into consideration. What they did, now they properly made a circuit, intentionally putting a galvanometer, and they brought up a magnet in its vicinity in this direction. The observation was, when the magnet is coming towards the loop, the galvanometer is showing a deflection. When the magnet is taken away from the loop, then this galvanometer is still showing the deflection, but this time the deflection is in opposite direction. The more fast, the more frequently, or the rate at which we bring this magnet closer to this loop, how fast we can do that. That means if this is magnet, I'm bringing it at very fast rate. So this speed was determining the extent up to which needle was showing deflection. That means if you bring it too fast, the needle was showing large deflection, and when you bring it too slow, this is T actually, you know, I have bad handwriting, so too slow, the needle was showing very small deflection. So these were the basic observations which was observed by Faraday, and these observations were later jotted down as Faraday's laws of electromagnetic induction. So what are Faraday's laws? See, I don't want you to write it down right now because this is again not in your syllabus, but you should know it, how electromagnetic induction works and on what things. So it helps us to understand the topic more clearly. So these observations were electromagnetic induction. What were these? Whenever flux linked with a coil changes, now what is where the flux is changing? What the observation was, when we are bringing this magnet closer to this loop, we are finding a deflection in the galvanometer. That means what is changing? Neither the wire has changed, nor the galvanometer, nor the magnet. Nothing has changed. The only thing which is changing is the number of lines, which is magnetic lines of force, which is passing from this coil. So suppose when magnet is far away, there are only 2 lines passing, and when magnet is closer, suppose there are 20 lines passing. So what is changing? The number of lines, which is number of magnetic lines of force. So whenever number of magnetic lines of force, which was flux, so whenever flux linked with a coil changes, an induced EMF is produced in it, which will last so long, the induced EMF will be present in the circuit according to observation. See, according to observation, the current was flowing in this loop only till the point when the magnet was moving. Till the point magnet is moving, you will see a deflection. You bring the magnet close and stop the magnet right here, the deflection will go back to 0. That means when a magnet is not in moving position, then there is no current in the circuit. So what does this gives us? That whenever flux linked with the coil changes and induced EMF is produced in it, number 2, this induced EMF will last only till the change in flux is continuing. We need to change the flux continuously in order to get the deflection, in order to get the current. So that is what electromagnetic induction is all about. Electromagnetic induction is the phenomena of production of induced current by changing magnetic flux or by changing magnetic field. Another point which you have to learn by heart, which is the observation part. The 2 observations was, you can write it down right now, that whenever flux linked with the coil changes and induced EMF is produced in it, whenever flux linked with the coil changes and induced EMF is produced in it, it will last so long as the change in flux continues. Alright, this was the observation. Now we are skipping the formula part. Again, I haven't seen it in NCERT, so I'm not going to give you the formulation for induced EMF, but we are going to discuss what would be the direction of induced current if we have a change in magnetic field. Suppose this is my uniform magnetic field. So now you know in which direction this magnetic field is. These magnetic lines of force are in vertical directions, vertically inwards. This is my loop, a current carrying, not current carrying loop, a simple circular conducting loop. I am bringing this inside the magnetic field. So initially when it is outside, when it is just outside this magnetic field region, there is not a single magnetic line of force which is passing through it, right? But as soon as it enters this region of magnetic field, what will happen? There will be change in number of lines passing through it. Initially 1 line will pass, then 2, 3, 4 and so on. I have represented just how many? 4 into 6, 4 into 5, just 20 lines, but actually magnetic lines of force are infinity, right? So the moment it enters the region of magnetic field, induced current will flow in the wire, and this induced current can have any direction, because in circular loop the current have only 2 options, clockwise or anti-clockwise. So we must have a definite rule to state in which direction the current will flow, and that rule is called Fleming's. Now again we have Fleming's. This time we have right hand rule. Now what is right hand rule? The right hand rule states the same. If you stretch thumb, first finger and middle finger of your right hand in three mutually perpendicular directions such that this first finger is giving you the direction of magnetic field and thumb is giving you the direction of motion of the conductor, then the middle finger will give you the direction of flow of current. So motion, field and current. Okay. Yeah, right. Now actually I was about to say that don't show the individual fingers for obvious reasons, right? So what are motion, field, current? In this case we have to find the direction of current given by middle finger. Take thumb as the direction of motion. Where is the direction of motion? In this direction. The loop is coming in this direction. Where is the field? Field is in vertically inwards direction. So current, according to the right hand rule, current is in vertically upward direction. That means in this loop current will start flowing like this. That is anti-clockwise. So this is how you find the direction of current. This is called induced current. This is not normal current. Induced current is the current which is automatically getting produced inside a conductor when it is entering or leaving. Whenever the flux linked with it changes, induced EMF gets produced in it. So whenever it enters or leaves the region, the current is going to get flown in it. Now we'll elaborate this rule. Fleming's right hand rule states thumb, first finger, thumb in the direction of motion, first finger in the direction of again magnetic field, then middle finger is going to give you the direction of what? Induced current. This whole phenomena is electromagnetic induction. So what is the difference between Fleming's right hand rule and left hand rule? Left hand rule was to be used for the direction of force which will be experienced by a wire which is placed in a magnetic field given by force, field, current. In right hand rule it is giving the direction of induced current and the right hand rule says motion, field, current. So now you see force, motion, field is same, current is same. The only difference, another difference is here we are finding out the direction of force. That means we are finding out the direction of thumb. Here we are finding out the direction of current, not thumb. So this is the current, or just see the difference. What I'm going to tell you is here you have to keep these two fingers aligned and thumb is going to give you the final answer, whereas in this case keep these two things aligned, that is thumb and the first finger. Middle finger is going to give you the direction of induced current. That is the basic difference between Fleming's left hand and right hand rule.